Prepare for an unfathomable disaster of extraordinary magnitude. Betelgeuse, the red Goliath star at the edge of our system, carries ominous messages across the universe. Using the James Webb Space Telescope, cosmologists have discovered something remarkably exciting about this massive celestial body. When the famous astrophysicist Brian Cox makes a serious confession, the question becomes unclear. Are we witnessing a catastrophic cosmic explosion? An explosion that could forever change the night sky as we know it? We must immerse ourselves in the wondrous fabric of the universe, where stars are born, live, and die in wondrous ways. One star has recently captured the imagination and concern of cosmologists and the public alike. This star is Betelgeuse, a red supergiant of enormous size and age, prominently located in the constellation Orion. Its unmistakable reddish hue and variable luster have long attracted interest. However, recent developments have increased interest in this celestial monster. As we explore the nature of Betelgeuse, we find ourselves on the brink of a potentially amazing event in the life cycle of this star. Betelgeuse, about 1,700 times the size of our Sun, is a celestial behemoth. Its immensity is almost beyond human comprehension. Imagine a star so massive that if it were to replace our Sun, its surface would reach beyond the orbit of Mars and swallow Mercury, Venus, Earth, and Mars in its celestial embrace. This amazing size not only shows the physical characteristics of Betelgeuse, but also represents its stage in the celestial life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a phase characterized by expansion and cooling after a lifetime of fusing hydrogen into helium in its core. Betelgeuse is believed to be approximately 8.5 to 8.8 million years old, relatively young in human terms but ancient in celestial life. Its current status as a red supergiant is the culmination of millions of years of stellar evolution, a period marked by dramatic changes and processes that transformed it from a hot blue star into the red giant we see today. The life cycle of stars like Betelgeuse is a story of change driven by the relentless forces of nuclear fusion and gravity. Betelgeuse's characteristic pink hue is another indicator of its current phase. The red color is due to its relatively cooler surface temperature compared to other stars such as our Sun. While the surface temperature of the Sun is approximately 5,500 Kelvin, the cooler surface of Betelgeuse registers a temperature of approximately 3,500 Kelvin. Because of its cooler temperature, Betelgeuse emits light at frequencies that give it a red appearance. But this color is not just a visual feature. It provides clues about the physical state of the star and its rotation in the vast expanse of gas. Betelgeuse's personality is enhanced by its historical variability. Changes in Betelgeuse's apparent brightness and its variability have long fascinated astronomers and skygazers. Betelgeuse typically goes through a cycle of 400 days, and a longer cycle that lasts about 5 years. These cycles were recorded as early as 1836, perhaps even earlier in the original oral traditions. But what really puzzles Betelgeuse is not just its changing brightness, but also its deviation. Unlike many stars that follow an expected pattern, Betelgeuse sometimes deviates from its rhythmic dimming and brightening, revealing complex and less understood processes in its epic structure. Recent groundbreaking discoveries have certainly caught the attention of cosmologists and astronomers worldwide, changing its appearance in surprising and dramatic ways. The event is now widely known as the Great Dimension. In late 2019, the red supergiant Betelgeuse, arguably the brightest star in the night sky and a prominent part of the Orion constellation, began to mysteriously dim. The star's dimming was so intense that it began to lose its brightness by an average of 0.01 magnitude per day, reaching its lowest brightness in February 2020. Betelgeuse, which is normally visible to the naked eye even in light-polluted areas, has dimmed considerably. The change is noticeable even to a novice observer. However, there is one problem with tracking Betelgeuse activity: lag. When we look at a star like Betelgeuse, we don't see it as it is now, but as it was in the past, because light takes time to travel. In the case of Betelgeuse, some 725 light-years away, the light visible today left the star nearly 7 centuries ago. This lag makes it difficult to predict and observe sudden changes in a star's behavior when we are essentially looking at its past. The Betelgeuse dimming event was a sign of the inherent difficulties of galactic observations and the limitations of our understanding of dealing with the vast cosmic scales and time lags they cause. Andrea Dupree, director of the Harvard-Smithsonian Center for Astrophysics, and her team closely followed the unfolding of Betelgeuse's celestial drama. They used the Hubble Space Telescope to analyze the behemoth star as part of a 3-year study to monitor variations in Betelgeuse's outer environment. These observations provided unique insights into the dynamics of a variable star like Betelgeuse, which is constantly expanding and contracting, causing changes in brightness. Hubble's ultraviolet light allowed scientists to study the layers above the star's surface, heated in part by the star's intense convection cells. A further survey of Hubble spectra in 2019 and 2020 measured the movement of material in Betelgeuse's outer atmosphere. Specifically, the spectra focused on the magnesium-2 lines, which describe the conditions of the star's atmosphere. These observations showed that material is moving at a speed of about 200,000 meters per hour from the surface of the star into its outer atmosphere. That hot, dense material eventually expanded thousands of kilometers from Betelgeuse and was the precursor to the dust cloud that caused the star to darken. Dupree and his team estimate that Betelgeuse's southern hemisphere lost about twice as much material during the 3 dimming months. This mass loss was significant, especially considering that, like all stars, Betelgeuse is constantly losing mass, albeit at a much faster rate than our Sun. The size of this massive explosion and the resulting dimming caused a debate among cosmologists as to whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, approximately 725 light-years from Earth, adds to the intrigue, as any such explosion would be visible from Earth and would provide a rare opportunity to observe a supernova up close. But what does this dimming event portend for Betelgeuse's future? Is this a sign of an approaching supernova or just an extraordinary episode in the long and complicated life of the star? Several hypotheses have been proposed to explain this sudden change. One prevailing hypothesis proposed a stage in the supernova explosion process, a theory that gained some traction when Betelgeuse was believed to be widely approaching the end of its life. Another popular hypothesis suggested that dust, perhaps from the star itself, obscured our view. Betelgeuse, like other red supergiants, can leak material, and that material is thought to form a dust cloud thick enough to drown out the star's light. A third explanation involved changes in the star's photosphere, or visible surface layer, that could affect its apparent brightness. Further studies using different observational methods solve this mystery. Spectroscopic studies showed a decrease in Betelgeuse's effective temperature, suggesting that the dimming may have been caused by a large dark spot on the star's surface. This hypothesis was supported by the observation that the temperature of Betelgeuse decreased by approximately 170 Kelvin at the moment of darkness, revealing massive changes on its surface.
Finally, the key to understanding this strange phenomenon came from humanity's guardian of space, the Hubble Space Telescope. Hubble's observations indicated that the dimming of Betelgeuse was probably caused by a massive ejection of hot material into space. This material formed a dust cloud that darkened part of the star's surface, effectively reducing the amount of light reaching us from Betelgeuse. The dust cloud is thought to have formed from superheated plasma ejected from a large convection cell on the star's surface and then passed through the hot atmosphere into the cooler outer layers. As it cooled, it formed dust grains that created a cloud that obscured light from about a quarter of the star's surface. Hubble's ultraviolet spectroscopic observations, which began in January 2019, were critical in charting the timeline leading up to Betelgeuse's dimming. Those observations identified evidence of heated material passing through the star's atmosphere in the months before dimming. In December 2019, several ground-based telescopes also observed the dimming of the star, especially in its southern hemisphere. This material, initially brighter than the star's normal luminosity, eventually led to a blocking shadow as it moved outward and cooled. It was assumed that this outflowing material and the resulting blocking shadow caused the star to suddenly dim. Using the James Webb Space Telescope provided additional information on the Betelgeuse dimming event. Thanks to Webb's advanced observation capabilities, scientists were able to observe the star's activity in unprecedented detail. Webb's instruments, specially designed to observe in the infrared spectrum, allowed astronomers to study the dust cloud and its formation process in more detail. The detailed data provided by Webb supported the hypothesis that the darkening was mainly due to ejected material from the formation of the dust cloud. Webb's observations also shed light on the star's outer atmosphere, where the dust cloud formed. By analyzing the spectral data, the researchers managed to determine the composition and temperature of the ejected material. These data helped to better understand the mechanisms leading to the mass extinction of red supergiants such as Betelgeuse and the role of convection cells in these processes. Webb's detailed images and data revealed the complex structures of the dust cloud, providing a clearer picture of how such massive ejections affect the appearance and behavior of the star. The dimming event is not definitive proof of an impending supernova, but it has certainly increased interest in Betelgeuse's future. A supernova explosion is the ultimate fate that awaits red supergiants like Betelgeuse when they exhaust their nuclear fuel and collapse under their own gravity. When Betelgeuse goes supernova, it becomes an astronomical spectacle on an unprecedented scale. The explosion is so bright that it is visible during the day and can outshine the full moon. The resulting supernova remnant is also the subject of extensive research that provides insight into the processes that govern the life and death of massive stars. However, predicting the exact time of such an event is still difficult. While the Great Dimming has sparked debate about the fate of Betelgeuse, it is important to recognize that stars of this size can vary greatly without immediately leading to a supernova. Betelgeuse's future is still uncertain, and it may behave erratically for centuries before finally exploding. Studying the Great Dimming of Betelgeuse has implications for our understanding of red supergiants and stellar evolution more broadly. The insights gained from this event have improved our understanding of the processes that lead to mass loss, the formation of dust clouds, and the dynamics of convection cells in these massive stars. These observations apply not only to Betelgeuse, but also to other red supergiants in our galaxy and beyond. Advances in observational technology, particularly the capabilities of the James Webb Space Telescope, have opened up new opportunities for studying the life cycle of massive stars. Webb's ability to observe in the infrared spectrum is a powerful tool for studying the dust and gas around these stars, revealing intricate details of their behavior and evolution. The data collected by Betelgeuse is a valuable reference for further studies of similar stars and their possible fate. Betelgeuse's Great Dimming event has fascinated the scientific community and the public, providing a rare glimpse into the dynamic processes inside the red supergiant. A combination of observations from the Hubble Space Telescope and the James Webb Space Telescope provided a comprehensive understanding of the mechanisms leading to this dramatic change. Although the exact timing of Betelgeuse's potential supernova remains uncertain, the information gained from studying this event has significantly increased our understanding of stellar evolution and the life cycle of massive stars. As we continue to observe Betelgeuse and other red supergiants, we may gain more exciting insights into the complex and dynamic nature of these cosmic giants. The Great Dimming event is a reminder of the ever-changing and unpredictable nature of the universe, where even the most familiar stars can surprise us with their dramatic behavior. Betelgeuse's story is far from over, and its future promises to be an exciting chapter in the ongoing saga of cosmic exploration and discovery.